Before we start, Sumati has a quick announcement.
Hi, can you hear me? Yeah. So one practical announcement. Some of you have signed up for the trip on Friday, and the person should be outside, right outside here. I haven't checked, but he wasn't here yet. Okay, so he will come sometime today. So please make sure that you pay him for the trip on Friday as soon as you can. When he does come, and I'll let you know when he comes. But also, just before we leave for lunch, I would like the speakers to, the ones who haven't been on panels or who would like to be in the remaining panels, to please come, because everything we had on the board was erased, so we need to reconstruct the panels, the people who are in the panel. So.
Sumati, that will be immediately after this talk and just before lunch. Is that what? No.
One more talk.
Ah, right. I'm sorry. Yes, forgive me. Great. So welcome back. And our next speaker is Ramadevi, and who works at Indian Institute of Technology, IIT, Bombay, India. And she will tell us about quantifying three manifolds.
Thank you. Been nice place, and thanks for inviting. And really, I'm enjoying a lot of new ideas, new themes. I'm sure. Still, I thought it is working. Bit closer. I did check once, and then I was. Is this okay? But in fact, I don't probably need a mic, but it's okay. Anyway, so this is something which I thought this topic is the right forum to present this work, because there was a lot of battle in understanding three manifolds from both mathematicians' view and also the physicists' view. And this did happen sometime in the 1999-2000 period, solved by an accident, and this problem has been lying with me from 1994. Okay, so it took about 6 years to really resolve this. I felt this is the right forum to talk about this, and this was a hybrid with one mathematician, Sumati Nayak, who was on sabbatical visiting TIFR when I was doing my postdoctoral in TIFR, and she was giving a set of lectures in knot theory. And then I caught hold of her and I said that I want to show that the paper in physics matches with the paper in mathematics, even though I have a feeling that it will match, but I cannot understand the jargons. So that's the way the interaction started. And I still hear from Swati that mathematicians community is not happy with the paper. In fact, Swati was also not happy when I said path integral measures. She said it is not rigorous, but she did agree to many of the results by her rigorous methods, which she took 3-4 weeks to calculate, whereas I could do it in 10 minutes. So she could see the power of how we use Chern-Simon's theory, and she admitted, and we wrote this explicitly in the paper, it is not rigorous, it is not, given proper, detailed mathematician's way of proving, but it did work. So I thought I'll give a glimpse of this work so that you will all enjoy the path switch. Okay, so my theme has been on quantum field theory, and interesting that Karen gave a beautiful talk showing quantum electrodynamics and all the diagrams, and then she went on to combinatorial way. There are various ways in which one could solve a quantum field theory. In fact, this has become a very important topic in this field, where you mix quantum field theory with topology in low dimension, and it has opened up a new field which is called quantum topology. So this is what we call it as a meeting ground for mathematicians and physicists. And I did mention during her talk, there are many open problems where we have a feel it should be, we conjecture a lot of things, to verify many of these conjectures. It appears that machine learning neural network approach seems to be the right direction, given it to be the topical area of research. Last few years it has started. Okay, so I just said, since I see that there will be many students and postdocs, even if they are not here, they are on Zoom, or they may hear the recording, there is a lot of challenging problems which one could get on to prove many conjectures, which cannot be done in our lifetime, but maybe using the machine learning tools can be faster to verify and so on. Okay. So let me start with some simple things. Orange today we got in breakfast. And the surface of the orange, just look at the peel, and that is what we call it as a two-sphere mathematically, and it is not required to explain it here. Of course, you can have also a genus, which is the donut. And you need to quantify that. We know that by squeezing or doing whatever, pulling, but not cutting, you can't go from one to the other. We know that, right? And we need a quantity. We know that the two-sphere, this is what we call it as a two torus. Usually we say it as a torus. Just look at the, don't include the, if you're looking at a cycle tube, don't include the air, just look at the surface. It's a two-dimensional surface. These two are inequivalent surface. You know it by just pulling, pushing, squeezing without cutting or snapping. But is there a mathematical quantity? And we have this mathematical quantity here. You can triangulate the surface, any of these surface, count the number of vertices, count the number of edges on those triangles which you have drawn on it, and the faces, and you compute this, which is what is called as the Euler character. So it's a very simple quantity to quantify that S2 is inequivalent to the torus. Okay. So this will be a genus 0 surface, and this will be a genus 1 surface, is another way of saying in topology. But this, by triangulating, you can show that this value is different for S2 and T2. And it's this quantity completely classifies all such two-dimensional surface. You can add punctures, you can see that there will be a plus h here added to the number of punctures, everything works. Okay. So the next question is, this is 2D surface. Okay. Do we have such a mathematical quantity for a three-dimensional manifold? Answer still an open question. It requires a lot of people to still find ways of finding an answer. So just to give you a list of three manifolds, the extrapolation of this two-sphere, you can look at it as a three-sphere. Okay, basically take R3 and look at all points at infinity identified with 1 point. So that says 3. You can also have a two-sphere, and at every point in the two-sphere you can put a circle. That's also a different manifold. You can have circle, circle, circle at every point. Or you can also mod out by a finite discrete group. Okay. I briefly mentioned, actually the group is such that there are no fixed points, and these are spaces for simple discrete, the Z2, Z4, they all become a class of three manifolds which is called lens spaces. Okay, so there is a whole list. I've just listed a few, but do we find some similar quantity which says that we know that this explicitly they are all inequivalent, topologically they are inequivalent, but you need a quantity which tells you that these are actually inequivalent. So this is a open question, simple examples. Yes, we have a ways of finding it, both mathematicians and physicists, but complete classification as 1-to-1 onto. You list the manifolds, you list any quantity, quantifying quantity. Are they 1-to-1 and onto? It's still an open question. Okay. I don't know how many of you have seen this fundamental theorem of Licorice-Wallace. So this was the starting point, the mathematician's theorem, which says that So in fact, Swati Nayak specifically tells me that I cannot say just a closed three-manifold. You have to give all the details. Okay, so even though I don't use in a physics sense all these things, I have to put in, otherwise she will be annoyed. So this is the way things are in the paper we had to write. So let me just stress that it was a good experience. It was also, it was delaying. A calculation could have been just immediately put, but then there was so many rigor which she wanted. And okay, any connected, closed, orientable three-manifold. I'm not a medical doctor, as some of them will say. We are all doctors, we are useless doctors. But what I mean is that we are not medical doctors. But the word is beautiful. They use the surgery. Surgery is like, I'll get back to all these highlighted terms, what it means. On a framed knot or link, and we're going to put this framed knot or link only in a three-sphere. Okay, so this is the beautiful theorem of Licorice-Wallace, that many three-manifolds can be constructed by this process. But what you need for this process is you should consider any knot or link in a three-sphere. Okay, so can we quantify this theorem? Just like you triangulate, put a vertices, edges, faces to quantify something, can we quantify this theorem? Okay. So before I get into quantifying, I'm just going to define one by one. All the highlighted terms I'm going to define. Okay. So all these highlighted surgery, frame, knot, link, everything I'm going to do. After that, if you still have questions, you ask. Yeah. Thank you. So that was just a theorem I put in. Of course, I'm not going to say what is connected, closed, orientable. If you have such questions, we'll talk after. Okay? Yeah. So what is a knot? Knot should be viewed as some kind of a closed curve is what I would say, but technically it is an embedding of a curve. And that curve is non-trivial only in 3 dimensions. Okay, if you draw some complicated knot, and if you are in 4 dimensions, you can remove all the crossings. Only in 3 dimensions, the curves which you draw is non-trivial, and it can be in any three-manifold per se, but for Licorice-Wallace theorem, we will take these knots to be inside a three-sphere. Okay. So for example, I've just drawn a simplest knot. At least at the end of this talk, you should know trefoil is the simplest non-trivial knot, and you can see that we draw it as a projection onto this board, and they have 3 such crossings. You can take a mirror image of it, then the crossing signs will change. Okay, so 3 plus 3 for trefoil and minus 3 for the mirror image and so on. You can show it by putting an orientation and looking at the handedness. Curve is just a circle, but it can be, because there is 3 dimensions, I can go inside out and come back. So it can be a non-trivial curve. Yeah. It's closed. Yeah, it's a closed. Knot is a closed. Yes. So it's a closed curve, or I should have said I should have said a curve as a circle, but okay. Yeah, it's a closed curve. Thank you. Link is nothing but a collection of such knots which could be entangled. If you're not entangled, you call it as an unlink. But this is the simplest. I put it by 2 different colors. So just to show that this is component 1 and this is component 2 and they are entangled. Okay. So this is a 2 component, and it is this particular thing which has a linking. It's called as a Hopf link. Okay, so the simplest analog of your Euler characteristic, for knots at least, you can say that there is a crossing number, there is a linking number, and so on, but they are all very poor invariants. There are many knots which have the same crossing number. There are many links which have the same linking number. So it's not a very good invariant. Okay. What is frame naught? Someone was asking. Frame naught has to be seen as projected onto the blackboard. Once you're projected onto the blackboard, you should not come out of the board. Okay. So for example, if I take this, I can't undo this crossing, which I could have done if I'm not projected onto the board. Okay, I can use the extra third direction and undo this. That's what is called Rejzner move, one of the Rejzner move 1. But I can pull and push this diagram. There are 2 specific Rejzner moves called 2 and 3, which you can use and you can equivalently draw this. Okay, I'm not done cutting or pasting. By pushing and pulling, not coming out of the board. Okay, I can do this, and these 2 are equivalent. And as I said, the crossing signs are not only this, but I have to also take care of the crossing signs of them. So if you add these things, it turns out that these are undoing, the crossing sign numbers, it becomes +1. So 3 minus 2 will be +1, and I call this as a frame trefoil with framing number 1. Is that answering your question to know what is a frame knot? Okay, fine. Yeah, correct, exactly. And surgery of this and surgery of without these things will give you 2 different manifolds. So the frame link is important in licorice vallis. Okay. So I take this let me take this telephone wires, I twist it, right? I just stick it to the board. Then to untwist it, I cannot be on the board and untwist it. I have to pull it out to do it, which means I need the third direction. If I don't allow the third direction, this diagram with framing 1 and the previous slide which I showed you, this is with only framing 3. There are 3 crossings. They are 2 distinct objects as far as the blackboard frame is concerned. But when knot theorists are looking at invariance for knot in 3 dimensions, whatever invariant you write for this should be the same for the other diagram. But for licorice vallis theorem, it is very important that you don't move out of the plane. Okay? So if I do it on a trefoil without those self-twist, I will get a different 3-manifold. If I do it with trefoil with self-twist, I will get another 3-manifold. So the frame link is very important. Is that okay? Yeah. So similarly, I put a boldface F because for every component of the link, like half link, I can put F1 self-twist, F2 self-twist, and so on. So it will be in general, if there is an n component link, there will be an n tuple of framing numbers which I have to write for each component. And it is this link on which I will do the surgery in general. Yeah, so you put the orientation here. If you put the forefinger on the overcrossing, then the undercrossing direction should be in the direction of the thumb. So then it is plus, plus, plus. And then go there, you will see that overcrossing, undercrossing is in the opposite direction to the direction of thumb. -1, -1. So it adds up to be. Is that okay? Is that clear? Okay. So surgery. No major surgery, but we do this as a prescription. Basically, what do we want to do? We want to take a 3 sphere and want to convert it, let's say, to S2 cross S1. Then you take specific knot or link inside S3, and then this is the procedure. You take a tubular neighborhood, you thicken it basically. Thicken it, make it like a tube. Okay? Show you some pictures. So take it in arbitrary manifold. I'm not specifying that this is S3. In any M, you have a curve. I'm just doing it as a cartoon diagram. take a tubular neighborhood of this curve, thicken it. And then remove this tubular neighborhood. Just remove it out. When you remove it out, each one is still a three-manifold, right? But it has some boundary, which is the boundary which will be a 2 torus. Okay? So this is what you will have. Fine? So this is, mathematicians calls it as, if C is a knot, then this is a knot complement. So this is a three-manifold with the torus bound. Okay? Okay, so now back to Licorice-Wallace theorem. I've defined for you what is surgery. I've defined what is the difference between framing the knot, frame knot or frame link. You can put it in S3. And now if you have many components of a link and each component could give you boundaries, you can choose it in such a way that the boundaries are all going to be disjoint. Okay? So these are things which is possible to do. Okay? So I'm just confining to a simple one curve, one closed curve. I'm explaining it here for S3. And this in quantum field theory language, we call it as a Wilson line or a Wilson loop. And you thicken it, take a tubular neighborhood, cut it out, and you had two pieces. If you paste it with an identity map, you'll get back this original diagram. Okay, is that right? You identify, there are two cycles, one is meridian and one is longitude. You identify longitude with longitude, meridian with meridian, you will get back your original manifold. This is just to, this can be treated like an imaginary curve and we don't need to worry about it. So it will give you the finally the three manifold. But I could do more. I could do many maps. I can map the meridian to longitude, longitude to meridian, right? This is the famous one which is called in a conformal field theory as a S transformation or S matrix. Okay, so I'm just writing the boundary of the knot complement in S3. I can relate it to this torus, write an S map, yeah. Exactly. I'll come to the definitions. No, I'm not. I'm only talking about the licorice theorem at the moment. I'll come back to, I'll first do this and then I will tell you how this is. Right now, yeah, I just said, I could have just said a closed curve here. No. Yeah, I'm yet to define Chern-Simons. I'm just getting all of you to sync to the notation and the story before I get on to more jargons. I hope I am not lost the audience. Okay, fine. And there could be a more general surgery where you take a linear combinations of this longitude, P times the longitude plus R times the meridian and map it to the longitude here or meridian here, and there will be another, it's an SL2Z transformation, the other two integers can be fixed. But this is what is known in the literature as P by R surgery, and many times this is a closed three manifold which is written as just like this is not complement. This can be treated as a P by R surgery on S3 containing a knot K, and this is a closed three manifold. Okay, so this is the formal procedure of getting new three manifolds. This one also will give you another three manifold. A trivial one, just gluing it will give you the same manifold. And we need to still find a methodology of finding the mathematical quantity analog of Euler characteristic, which will help me to do this. Okay, so this I'm pulling out from the literature of mathematicians. Simple Yeah, so I'm explaining it to you. We'll see this. Yeah, what exactly? See, I'm going to take a knot or a link. I can start doing surgery on. And I just explained the diagram with the knot for simplicity, but you could have done the surgery on this 2-component link also. And what I'm saying is that you first take the link complement of this, and then you do an S mapping, which is meridian to longitude, longitude to meridian on each of the toral boundaries. And then you will end up getting a new 3-manifold, and that new 3-manifold turns out to be S2 process. Okay. So what is this table tells you? If I did a surgery of just a simple curve, I would have got S2 process 1 by the S map. If I did the surgery of this 2-component curve with these specific framing +1 here and +1 here on the 2 components, I will get the same 3-manifold. Yeah.
How does the surgery depend on the framing?
No, now once I put it on the blackboard, I cannot undo this crossing. That is why it's called a frame link.
I understand that, but the description of surgery that you gave
Yes.
was entirely within the 3-manifold. There was no, there's nothing.
It's still on a 3-manifold, but what I will make sure that this curve, and if suppose the curve is like this, suppose I take this curve, I will not change this curve because it is in a 3-manifold and remove it. I will take this to be the frame knot. This is frame knot with framing +1, and that is frame knot with framing 0. Topologically is because you're taking the third direction, but Licorice-Wallace theorem says that you cannot undo this extra crossing when you are doing the surgery. If you do with the surgery with this, I will get a lens space. It's a different manifold, RP3. Very different. That's the definition of Licorice-Wallace theorem.
So there's something about the gluing. The gluing back
nothing
must
to do with the
depend
gluing.
on
If
this
I take this
frame.
knot or if I take this knot, I will get 2 different manifolds. Gluing will be by the S. Not really. No, no. The boundary will have one extra self twist on it. It's like the T transformation which takes, it's very different. Yeah. The map which I will write here will involve STS or something. It becomes different. Diagrammatically, pictorially, what you're saying is what all of us think, and that is what Jones polynomial will be. If you write a Jones polynomial for this or a Jones polynomial for the simple curve, it will be 1 because Jones polynomial for the simple curve is 1. But Licorice-Wallace theorem requires you that you should not do the Reidmaster move 1. And that does change the boundary because you are mechanically doing it. This is allowed topologically in 3 dimensions, but you are not allowed to do it. Okay, fine. So this slide is mainly to show you that this diagram which I have drawn here, this, if I take this and if I do an S map, I end up getting back the S thing. So it's interesting to see that there are not just one unique knot or link giving you. It's not a 1-to-1 onto map, right? There are, at least I've listed 2. There is more to the list. There are many to 1 map. So even if I write the knot invariant for this, I have to use this modulo many to 1 map to define a quantity which will be a good quantity to say that quantifies this 3-manifold. Yeah.
I were to thicken these knots, right?
Yes.
I mean, I'd make their own tubular neighborhood
Correct.
in say R3.
Yes.
Then in that case, it looks to me that when you have these little twists,
Yes.
you're doing what we might call the Dane twists on the.
Exactly.
And
Yes.
can one think of it as these are the guys who are going to get embedded, mapped onto the boundary of The
Exactly.
boundary, the T2 boundary.
Yes,
Okay.
they
All
get
right.
mapped
So I
onto
think,
the,
okay, so
yeah.
I think that.
They get mapped onto the T2
So
boundary.
these are Dane twisted
Yes.
tori, which are now going to be mapped.
Sure.
Okay.
Yeah, yeah. Okay. So framed link corresponding to a manifold, even though I've put some simple examples, there is this one, there is actually a whole list. I didn't want to clog this slide, but you can see that at least for some examples, I've shown you that it is a many to one map. So it is frame. Suppose I know the invariant for a framed link. Can I generate the invariant for a manifold M? It is not one-to-one onto, it is not unique. But interestingly, that non-uniqueness can also be fixed. This is also by Kirby calculus. It's also the mathematicians' work. I've just shown it as a cartoon diagram here. You could put many such strands here and twist that many strands here and add an additional strand here. Okay, so this is an additional strand. And these two removes the non-uniqueness completely. Beautiful, you know, it removes the non-uniqueness completely. So what is that strategy to quantify Three-Manifolds? So I need to write an algebraic expression, just like Euler characteristic, some quantity I have to write. And there I will utilize the Licorice-Wallace theorem. So basically I should have polynomials of links, specifically framed links, not just all the polynomials, Jones polynomials and all are not for framed links. Even if you undo that extra twist, you get the same Jones polynomial. I want it to be a framed invariant. Then only I will start seeing this. And it is not difficult. There is a framing factor which we can put with Jones polynomial to take care of it. And of course, to get the three-manifold, you have this S map or P by R surgery map and so on, which is also can be called as a Dent twist. So those are the homeomorphic maps. And whatever expression I write, I have to make sure that if I worked out with, in the previous diagram, if you see it, if I work it out for this, or if I work it out for this, I should get the same answer. Then I can qualify it to be a three-manifold invariant. Okay. So it should, expression should not change under Kirby-Moos. Then such an expression qualifies to be a three-manifold invariant. There could be accidents. After we do this, still Jones polynomial, which is written modulo readmaster move 1, 2, and 3. There are some knots which accidentally becomes the invariant becomes equal to that. That I cannot help, but at least this is a basic requirement to make the invariant, which I can write an algebraic expression, which will be qualifying to be a three-manifold invariant, and that is quantifying this. Okay. And thanks to its talk today, Karen. So it's something similar, but not exactly. There was also one more, and she had a graph invariant here, but we are more interested in a specific crossing, which is an overcrossing. We don't put any orientation in the bracket polynomial. And you can recursively solve this at every crossing and write the invariant for framed links in variable A. Okay. And this can be shown to be proportional. I said that there is a framing factor, and this is the crossing number or the crossing sign, which people call it as right. And usually Jones polynomial is in a variable Q, and the Q variable and the bracket polynomial variable A are related by this change of variable as A equal to minus Q to the power of 1. Okay, so it is this neat that bracket polynomials can be computed if you know Jones polynomial, and the knot atlas and various websites are there where all these data are available for any of many of these knots. Okay. There is another alternate way in which these invariants can be computed, and that is from a specific quantum field theory, which only captures the topology of knots, links, and three manifolds, and that is called Chern-Simons field theory. And if it is going to capture invariance, it should include the well-known polynomials. The well-known polynomials are Jones, and there are many more new polynomials which we could generate. Okay, so then that brings me to your question of explaining what is a Wilson line, and I'll give you a brief overview. For many of you, I'm sure many of you know it, the Simons, so this is what was initiated by Albert Schwartz. So sometimes Chern-Simons theory is considered to be a Schwartz type topological field theory. And Simons and Chern introduced a specific volume term, which is the action for the Chern-Simons. It's called as a three-form term. And by the way, this is the Simons Foundation person, founder, the same Simons. And when I was in Warsaw, that's the time, we got to know that passed away. And he's the founder of Simons Foundation. I don't know how many of you know it, but I thought in this forum I should flash this. Okay, and this is the father who has really worked on this interface of topological quantum field theory to many low-dimensional answers to topology and geometry in low dimension, Edward Witten. And the starting point, which annoyed Swati Nayak, is this partition function. He was not at all happy with this measure. Okay. Of course, in all our any field theory computation, these are what will be computed, giving you the vacuum diagrams or the bubble diagrams with no external legs. And if you put external legs, you get correlators. So I'm not getting on to the field theory computation. My focus is what exactly was the problem we solved. But clearly, this left-hand side quantity should be an algebraic expression to capture the three manifolds. Because this is a topological field theory, this topology, the partition function should give us a topological invariant of a three manifold. And this integration of the three form action, that's what on a three manifold, and this is what gives you the topological invariant of the three manifold. Okay, so just to put you, many papers, any places you would have heard that it's actually proportional to a WRT invariant, Witten-Reshtchev-Thoraev invariant. And the next question is, we are not only interested in partition function in any field theory, we are interested in observables, like the 2-point correlators which he was drawing. These are the Wilson lines in the field theory. And then you can ask the expectation value of those observables should quantify the knot polynomials, well-known knot polynomials, and other knot. Okay, so coming back to the formal definition of what a Wilson loop is, I'm going to confine myself to a theory with SU2 gauge group. So these Wilson lines can carry the spins of the SU2, spin half or spin 1 and so on. So this R can be treated like the spins of the SU2 put on the Wilson line. And formally, you have to write, which is not going to change when you change the size of this object. That's why it's topology. It's a topological invariant. A tiny looking object like this or a bigger form should not give you a different answer. And those are taken care by this Wilson loop operator, where the tracing is over whatever we call it as color or spin in SU2 context, and you have to trace it over, and then this integral is over this closed curve. Okay, is that answering you? This integral is over this closed curve, and this is the gauge field, and these are the generators of the gauge group which we take. So formally, you can take this, call that as an expectation value of such curves, and find a quantity. And if I put this R to be the fundamental representation of SU2, So if I put this to be a fundamental representation, or you can call it a spin half representation, we generate the Jones polynomial. So that's another way of saying we have a three-dimensional definition of the recursive method of writing the Jones polynomial directly using Chern-Simons theory with SU2 gauge. Okay. And if I put spin 3, spin 1, spin 3 by 2 higher rank representation, but still keep it as SU2, then there is a whole list of colored Jones which one could generate. And there is this variance, you can change the group to SUN and so on. This is where so many mathematicians had independently done the work. So this is now famously called as home fly PT. And then the higher symmetric, anti-symmetric, mixed representations are called the colored home fly PT. Okay, so some of the puzzles are still being tackled. Any polynomial you write, the coefficients are always, it's a Lorentz series with coefficient always integers, whether it is fundamental. So fundamental, I'm not showing that representation, but fundamental is what they call it as Jones for the SU2. And colored, we put this representation just to remember that the n in the Young diagram language is n minus 1. So the Jones will be J2 and so on. Okay. Fine. And framing invariance even for colored can be written involving a piece which is going to be dependent on the right of the knot. So there is a way of writing this. So in some sense, we have all the methodology where how bracket polynomial with the change of variable as a equal to minus q1/4 can be written where all the component knots carry the fundamental representation. Okay. So this is something which we all know. And still the puzzle is two different looking invariants of a mathematician. So there are two invariants in the market. One is licorice invariant. Licorice invariant. So I'm going to confine myself to three manifolds. I'm not explaining how we get the knot polynomials. That's a different separate talk it can be. But my interest is assuming those polynomials which I can compute in Chern-Simons theory. And there is a different way in which the three manifolds are obtained. I want to reconcile both. So what these guys have done, what Licorice paper has done is he used bracket polynomial. He also had to introduce cables of the links. So just to give you a simple picture, if I took this diagram, if I want to make it two cable, I just duplicate two curves and draw this over crossings. Okay. If I want to make it three, I will draw three lines and go do this. And this was forced to construct an algebraic expression for the licorice. Okay. And formally, I'm just writing. I'm not saying what those coefficients are. This depends on the cabling factor, and lambda is some function of those cabling factor. And then this is the bracket polynomial of such diagrams. You can see how tedious it is. Even for the simple knot, you know, the next one will have 4 crossing, the next one will have 9 crossing, and I have to go through the C over a representation. Sorry, C is just the numbers, 1 cable, 2 cable, 3 cable, and so on. And A, if you specifically choose it to be 4rth root of unity, that summation range can be taken from 1 to r minus 2. And it is doable. Okay, we can do it for r equal to 5, r equal to 6, and some simple low crossings, this can be computed. And with the change of variable, q being, a being minus q to the 1/4, we can try and see how my Kaul's invariant. So Kaul also, Ramesh Kaul was one of my collaborators, and he had come up with a nice, neat invariant using SU2 Chern-Simons invariant, but colored, all the colored, not just Jones, colored Jones So if, for a simple knot, you will have a summation, and this summation is also truncated. You can see that there is a lot of similarity. There it was 1 cable, 2 cable, 3 cable. Here you see that it is spin half, spin 1, spin 3 by 2 and so on. And there is a cutoff, and this cutoff is given by, this is what we call it as Chern-Simons coupling or a level K. Okay, so there's a lot of similarity. So this was the thing which bothered me from 94, 95. These two are looking really close, but how do I show that these two are equal? Okay. So what we did is, this was our guess actually. We thought that if I replace this by a double cable, I thought it should be like a tensor product of spin half, which is very familiar to many of us who do quantum mechanics or atomic physics or nuclear physics. And what they call it as cabling, I thought it should be a tensor product. Had enough details on finding the representations of braids for tensor products. I had a lot of details. Not going into the details. So what I showed is, or what we showed, basically I gave her a 3 cable trefoil and asked her to work out the bracket polynomial. And I gave her an answer using tensor product in probably 5 minutes. And every sign, every factor in the 3 cable of a trefoil matched. Then only she started thinking, I believe you. And then the collaboration continued. I'm sorry, but I will take probably 3 to 4 minutes. Is that okay? Just 3 to 4 minutes. So indeed, we did this rigorous proof. I know I switched to those days HRI for a postdoc, and I was telling Ashok that for every R and every K, I could show for some 100, K equal to 100 or R equal to, I could show that these two are matching, but I didn't have a proof, but he gave me a very nice way of proving that it is true for arbitrary R and K. And that was very neat. And then indeed the paper appeared in the archive where we actually showed that both different looking three-manifold invariant, one with cabling, another one with higher colors of SU2 represented. Higher colors means spin half, spin 1, that linear combination. Those two are actually one and the same. Okay, so this is what this is. Thank you.
So you started off the talk musing about using machine learning methods to solve some of these problems.
Yes.
I'm not immediately seeing, like from what you presented here, how, where machine learning can kind of sink its teeth in. So I was wondering if you could just say a little bit about.
See, I basically K, from Chern-Simons theory, the K, which I said coupling constant, has to be an integer, a positive integer. But interestingly, we can do analytic continuation of K and make it even complex. And we wanted to check hyperbolic quality. There is one paper already on the archive. In fact, it's also published with Vishnu Janjala and the team who work on heavy duty on machine learning. And we showed that for some rational value of K, which is not physically meaningful as far as Chern-Simons gauge invariants are concerned, we could get with very precise, with some little errors, the hyperbolic volumes of many knot complements. So, and they did this 5 years ago for spin half, and then they didn't have the data for spin 1, and we could generate with my former students who are postdocs now, Vivek and various team, that we had some 2 million data. And then they showed that we could conjecture for any color what should be the volume, hyperbolic volume related to the what K value. And we are still verifying it for spin 3 by 2. So some of these things, because we could generate the data for other colored zones, we can actually verify. There's also another one is unknotting, which is still an open question. I think there are some generated things that given a complicated mess, can you see that it is actually going to have the same Jones polynomial as an unknot? That's still an open question. So a lot of things are there. There are a lot of conjectures. Yeah, Sergei Gukov has a team who are looking at many conjectures where he himself feels that only through machine learning and artificial intelligence algorithms, many of these conjectures can be proved or disproved. Okay, so that's why I'm motivated.
Yeah.
Yeah, thanks. Yeah.
Thank you for your talk. Is the fact of having two ways of seeing the same invariant,
Yes.
does it have practical consequences? Is it easier to distinguish frame knots using the new way of seeing them?
See, here we use the frame knots, right? When we compute the three-manifold, so if frame knots, two different frame knots share the same frame link polynomial. For example, there is a piece, it's like, during COVID times when I say people get angry, but there's something called as a mutation. What is mutation? Mutation is something where, let me just put it as an object here, which is a two-tangle. When you do a mutation, it can become like this. Just a 180-degree rotation about, let's say, this axis. Okay? And I fit back with the other pieces. Unfortunately, all the known polynomials, Jones, Homfly, Hoffman, don't see this mutation, don't see this operation. And if I use this knot or the other knot and I do my three-manifold invariant, they are not related by Kirby moves, related by Kirby calculus. Kirby moves, this mutation, these two knots are not related by Kirby moves. So they have to give me two different three-manifolds. But because the link invariant or the knot invariant for the knot and the mutant of that knot are the same, my expression will give me the same answer. That's why it's still an open problem. The expression which I write as summation over n mu of a with some coefficient, let me not. Okay, so this is the link invariant. I'm just putting only the room part for you. Okay, these two are same. But this manifold is M1, this manifold is M2.
So there's something I'm misunderstanding. What's the advantage of seeing this frame knot invariant from another point of view as you've done it? Oh yeah, sorry. I think I haven't quite understood.
What we were stressing, the fact is licorice method of cabling is very tedious. Because the cabling, even for trefoil, it took 3-4 weeks.
Okay, so
when we did by colored Jones from Chern-Simons, it's much easier.
It's much more efficient.
Yes,
okay.
It's much more efficient.
Okay.
But to show that these two are one and the same, we had to give a formal proof, even though we verified for trefoil, but we had to do it for many cases. And we could give a formal proof that these two are one and the same.
Okay, thank you.
Yeah.
So in view of time, maybe we can save further questions to the coffee break. So let's thank Ramadevi again.
Thank you.
So let's have coffee and come back at 11:30. I think we'll just have to eat in 10 minutes into